to this example equation over here, x squared plus y squared minus 4 is equal to 0, then let's work with that. Okay. So f of xy, now x squared plus y squared minus 4. So df dx is what? Is 2x. And df dy is what? 2y. Alright, so then dy dx is going to be minus fx over fy, so it's just going to be minus x over y. So let's pick a particular point. This point, x is 0, y is 2, then at this point, df dx is equal to 0, df dy is equal to 4. So everything works out here, that we do have a well-defined dy dx. Oh, just from a picture, from a graph you can tell what dy dx is going to be. What is it?
Circle?
What? No, but 0. But so dy dx at this point is 0. We have a horizontal tangent, and that's also what this formula would give you because df dx is 0. On the other hand, if we look at this point, x is 2. Y is 0, then fx is going to be 4, fy is going to be 0, so we have minus 4 over 0. We don't have a dy dx at that point. So around here, y is not a function of x. The conditions of the implicit function theorem don't hold. And you can see that if you look at any portion of this curve that contains this point, what we have here is that this curve does not pass the vertical line test, which is necessary for the graph of a curve to represent a function of x. So you see the consequence right there of when the requirements of the implicit function theorem don't hold.
Couldn't it be said that any point on that graph though doesn't pass the vertical line test?
No, because what I can do, I could take from here all the way over to here, just this part of the curve.
Okay.
Yeah, passes the vertical line test. Not the horizontal line test. So at this point, I could not define x as a function of y. So any point other than these 4, I could go either way. Y is a function of x, x is a function of y. But the implicit function theorem, this is a very local theorem. It's only saying what's happening near that point. You may not be able to wander very far from that point before things go wrong. So it's only making a statement about that point and extremely close to it. That's where you have guarantees, at least. Any questions about this one before we jump to free variables? So, now the implicit function theorem, I've only stated it for this one case, function of two variables. But what if you have z being a function of x and y? Defined by an equation. What happens in that case? For example, find this function, f of x, y, z is x squared z plus z squared y minus 2xyz plus 1 is equal to 0. And we have, make a z look more like a z. Okay, I guess I should do this. I don't really like doing this, but it'll work. So let's pick a particular point that satisfies this equation. So that would be x naught, y naught, z naught is 1, 0, minus 1. So the graph of this, of the solution of this equation, this point is on it. So we want to know, is it possible to implicitly define z as a function of x and y near this point? And if so, what are the partials of z with respect to x and y? How can we go about computing them? So what we can do is apply the chain rule to this function, differentiating it with respect to x, and then we can go back and differentiate it with respect to y. So f of x, y, z is equal to 0. It means we take this equation and differentiate it with respect to x. Now using a chain rule, as opposed to actually doing implicit differentiation, what we get is fx plus dx dx plus fy dy dx plus fz dz dx is equal to 0. Now partial of x with respect to x, that's 1. Partial of y with respect to x, 0, because x and y are independent variables. They do not depend on each other. So if we simplify this whole thing, we get fx plus fz, partial of z with respect to x, 0. So now we can compute dz dx. So it's minus x fx over fz. So whatever variable is a dependent variable, z in this case, it was y before, the partial of your equations function with respect to that variable, the dependent variable, cannot be 0. So as long as it's not 0, you can define this dependent variable as depending on the independent variables, x and y in this case, and you can compute their partial derivatives. Similarly, dz dy is minus fy over fz. Okay. So, in this case, if we go ahead and compute the partial derivatives, so we're going to have with respect to x, 2xz minus 2yz, and then fy is going to be z squared minus 2xz. Okay. And then fz is going to be x squared plus 2zy minus 2xy. All right. Okay. Now, so now what we could do is let's go ahead and plug in our point here. X naught, y naught, z naught is 1, 0, minus 1. So what we're going to get here is